Good morning, Go West Conference. I'm Takuto Nagami, as Boston introduced, a university student visiting here all the way from Japan. So today I'll be talking about the fundamentals of memory management in Go, learning through its history. So let me start with a question, classical presentation technique, right? So how many of you are new to memory management or have ever struggled to learn it? Could you raise your hands, everyone? Not everyone, yeah. Yeah, so I see many of you raising hands, nice. So honestly, I struggled with the memory management too when I first learned it. It's actually tough. Why should we care about it despite its complexity? Well, there are some reasons. First, knowing memory management helps you make your apps faster is a performance problem. Second, Go itself needs people who understand it to keep improving it. So if nobody knows about the memory management, who is going to take care of Go itself? And finally, it can actually be fun to learn Go memory management. Out of these, performance is the biggest reason, I guess. Cybergen, a Japanese tech company, once shared that just one small change in the memory allocation cut a CPU usage by 57% and the memory by 99%. That's massive, right? So I'll talk about this case concisely later. So if you've ever been curious about the memory management, you might have checked out some conference talks like Understanding Allocations, Memory Management in Go, the good and bad, Escape Analysis in Go, or Garbage Collection Schematics. But honestly, those can be really tough for beginners. Why are they? I think it's because of how we learn things. I like to call it the why, what, and how process. So think about that. So when you add a new feature to your application, you start with why. Why do you need it? And then you move to what. What exactly is it? And finally, how. How will you build it? I guess the reason most talks are difficult is that they jump straight into how the memory management. That's great for advanced golfers like pro golfers. But for beginners, it's just too much. So beginners first need the why and the what of the memory management. And that's what I will cover today. So keep that in mind. I am here to tell you about whys and whats of memory management in Go. So before we dive straightly into the memory management, so let's make sure that we understand two key parts of Go: the compiler and the runtime. The compiler's job is to take your Go code to turn it into the binary. So when you run go build command, that's what happens. Your code is translated into something the computer can execute. So everything that happens before you run the code in the build time is a compiler's responsibility. Once you actually run the binary, the runtime takes over. The runtime runs together with the program. It is compiled together with the program and runs together, and provides features that only work during executions, like scheduling Go routines or so. If you've wondered what the Go run command is, it's just a shortcut. It builds your code and then immediately executes the binary for you. That's simple, right? So we understood the compiler and runtime. And let's talk about what memory actually is next, the starting point of memory management. So if you build your own PC, you've seen it. So memory is those electric chips called RAM, random access memory. Now, some of you might think of a hard disk as SSDs when hearing memory, but those are strange, not typically memory. So when we say memory, we usually mean RAM in this session. When you run a program, the OS operating system splits RAM into the virtual memory for each process. I won't dive into details today, so just Google virtual memory later if you're curious. So you can think of the virtual memory as a key value store. The key is a memory address, and the value is a single byte. So unlike normal KV stores, the value size is fixed to exactly only 1 byte. When you write assembly, you work with this key value store directly. When writing data to the memory, you store the value at a directly specified memory address. And when reading from the memory, you retrieve the value from the address. That's simple. But this is actually painful because you would have to remember every single address while you're programming. That is a nightmare. Your brain explodes. To solve this problem, we now enter the era of variables using the concepts of stack and heap. So after the assembly era, the high-level languages appeared. So in 1957, Fortran, the first high-level programming language, is released, followed by COBOL, BASIC, Pascal, and C, and eventually Go. So with these, we gained powerful new tools. So many of the high-level languages, including Go, introduced variables as a form of data abstraction. When you declare a variable, say A here, the language somehow assigns it to some memory address. And the same happens when you declare B. As programmers, we just work with the variable names. That's perfect. We don't have to worry about memory addresses. That's a huge relief for programmers. But the language itself still has to manage where the data lives. The language can't just put data anywhere. It needs rules to place it properly. So we don't want to arbitrarily decide which memory address stores the variable data. Now, to make rules to place in variable, let's look at the function calls. The main function starts first, then it calls A, the execution moves there, A calls B, and the execution moves again. When B hits return, it goes back to A, same again, and finally back to main, and the program ends. This pattern is last in, first out. So the last function called is the first to return. So if you're an enthusiastic lead coder, you may have guessed it, is a stack data structure. And that's how the stack memory area was born. So let's see how variables are handled with a stack memory during the function calls. When main starts, the language creates a stack frame. A stack frame represents a function in the memory. Each frame defines a scope, so the language focuses on one function at a time. So here's a structure defined by the interface called ABI. You can search it on Google. So if you're curious, just Google it. So the important part is the variables declared in the main function go inside this frame if it is own data and address. And it gets tricky. So when main calls a function, the language knows the place where the call happens so that it knows where to return afterward. Then it creates a new stack frame for a function and moves the scope there. The language doesn't need to worry about the other frames at this point, like main stack frame. It just works with the current function. Before actually executing a code in the a function, the language knows the address of the previous frame, so it can come back smoothly. Arguments are copied in as variables. Then the code runs, and any variables declared in a function are stored in the stack frame. So when A calls B, the same thing happens. Note a call, create a new stack frame, store the previous frame's address, copy arguments, and run the code. That's simple. And when B reaches its return statement, the return value goes to the small CPU memory area, not a stack. I'm not going into the details about that. But after saving the return value, the B stack frame is completely erased, and the focus comes back to the A stack frame. So now the stack is A function. So control returns to A, which also returns a value, and its stack frame is then erased as well, and the return value is assigned to the variable in the main function, as you can see. So finally, the main finishes, all stack frames are erased, and the program exists. That's generally how stack memory area works. So far, stack seems to be perfect, but it's not a silver bullet at all. So stack allocations are determined at the compiler time, actually. Variables with unknown data size at compiler time, like maps or slices, as you can guess, are too complex to handle here. And stack isn't good for sharing variables between functions. You would have to copy variables as arguments one frame to another, so which makes the process slower. To handle the stack limitations, we use dynamic memory allocation, so-called a heap. So let's see how it works. When main function starts, its stack frame is created, as we see before. But if you declare slice, for example, here, the actual data goes to the heap. The heap is like an assembly memory. Data can go anywhere in the heap area. Unlike the stack, the language runtime decides the address. But here's the problem. Main function doesn't know where the heap data lives. So since the program focuses on main stack frame, it can directly address the heap data. And here's the solution. The stack stores a heap address in variable called the pointer, as we know. This pointer acts like a normal variable in the stack, letting us access and manage heap memory safely. This pointer is an important concept like talking about memory. Let's understand what pointers do with another example. So pointers are not just about a heap. So they're also the great tool for explaining the difference between the pointer arguments and the value arguments in Go. So with a value argument, when you call function, the data is copied into the function stack frame. Any changes inside a function only affect to that copy, and original variable in main stack frame stays the same. However, with a pointer argument, the function receives the pointer to the original variable in the main function. Now changing inside the stack function directly affects the variable in the main. So this is the difference between the value arguments and pointer arguments in terms of memory. So far, we've seen how stack and heap together make a general purpose memory management possible. Let's go back to the heap for a moment. So in the old days, especially in C language, heap management was done with two functions, malloc and free. So malloc is a function to allocate memory on the heap and returns a pointer to it. When you are done with the heap data, you have to manually call free function to release the memory so that it can be reused. But what if you forget to call free after calling malloc? So as you can guess, the memory usage just keeps growing. So this is called a memory leak. And in the end, the memory leak happens, and the problem just gets killed by the OOM, the auto memory error. To solve this problem, engineers came up with the automatic heap management, what we call now the garbage collection. Garbage collection, also known as GC, basically cleans up heap variables that are no longer in use. So it doesn't touch the stack. This is purely a heap thing. The Go includes the garbage collector in its runtime. It uses an algorithm called mark and sweep. Here's how we can think about the memory now, talking about the garbage collection. So instead of a tall tower we saw before, let's imagine it as a simple 2D map, since we don't care about the exact memory address anymore. So how does mark and sweep actually work? In mark phase, the runtime follows the pointers from the stack into the heap. So any heap variables reachable from the stack are considered in use. For example, if the main stack frame has a pointer to A gets marked. B is pointed, B gets marked too, and so on. Now we see E is pointed from the D in the heap, so E gets marked too. Basically, every object reachable from the stack is marked as a line. Then comes the sweep phase. Anything not marked in this example, C, is cleaned up. That's it, a very simple idea. But optimizing this algorithm is a bit tricky. The Go team has been putting much effort to optimize GC. For example, GC now runs concurrently with your code using techniques like Dijkstra's tricolor algorithm. You can also tune the trigger of the garbage collection with settings like Go GC or Go mem limit. And in Go 1.25, the brand new experimental algorithm called green tea was introduced. This green tea is an algorithm that makes the mark phase even faster. Actually, Go doesn't chase overly complex algorithm to go above and beyond, like other languages does. So Go keeps its GC simple, which really shows its philosophy, not only in the language spec, but also in the runtime. So far, we've seen that garbage collection is great for programmers, but it also brings some pain. So placing a lot of data in the heap can make the GC expensive. It uses a lot of CPU, especially during the marking phase. Most garbage collecting languages decide what goes into the heap based on the type. So in old Java, all objects created from the classes go into the heap. Python does the same. In JavaScript, all non-primitive type values go into the heap since it's not fully object-oriented language. So in many GC languages, non-primitive types end up in the heap by default. And this is where Go is different. Few languages, including Go or modern Java, has a special functionality called a heap escape to decide which variables really need to go into the heap. Heap escape in Go basically tries to keep as much data on stack as possible and only let variables that really need it escape to the heap. You might wonder, do we know which variable escape? The answer is, you don't. As Jacob Walker said at the GopherCon Singapore 2019. So there are some common cases where variable escape, like returning pointers, interface interface types, maps, channels, strings, and multiple slices. But beyond that, only the compiler and runtime to really know. Most heap escapes are determined by the compiler. The remaining ones are handled by the runtime. Though we cannot always imagine it, we can see how the compiler and runtime decides heap escapes. At compiler time, Go runs heap escape analysis to determine which variables should be allocated on the heap. So you can see the compiler's decision by adding the gc flags equals -m option to go run, go build, or go test command. This only shows the escapes decided by the compiler. For allocations, including those handled by the runtime, you can check them using benchmarking. So simply write a benchmark like this and run go test -bench package name and the package path and the -bench mem. So I brought some examples of heap escape analysis. First, a value returned from the function. It is a very common case that compiler says it escapes to the heap. And actually, benchmarking confirms it does by showing one heap allocation per operation. Next, the variable used only inside a function. The compiler says it doesn't escape. This pointer doesn't escape. And benchmarking shows 0 heap allocations, like you can see here. And there are some tricky cases. Sometimes the compiler says that the variable does not escape. Yet benchmarking reveals that it actually does because the runtime forces it to escape. So for example, a slice here doesn't appear to escape in a compiler log, like here. It says it does not escape, but benchmarking shows it actually causes one heap allocation per operation. So this is how we can observe how both compiler and the runtime handle heap escapes. By the way, let's take a quick look at how objects are all organized in the heap. So heap objects can have different sizes. For example, integers and pointers are 8 bytes, struct depend on their fields, and so on. To simplify the management, Go groups objects of the same size into the group called spans. So for example, here, span 1 might hold integers of 8 bytes, while span 2 holds structs or other 8-byte values, and so on. The grouping depends on the size of the values, not their exact types. Spans are grouped into M-central, and several M-centrals form an arena, and arenas together make up a M-heap, the complete heap area. This hierarchy helps Go manage memory efficiently. When we talk about the heap escaping, zero allocation is an important concept. Some libraries advertise themselves as zero allocation, but that doesn't mean no memory is used. So it really means no heap escapes. Data stays on stack instead of going to the heap. So there are several zero allocation libraries like Zerolog, zero allocation logging, fast HTTP, partially zero allocation HTTP server, or Go reflect zero allocation reflection, surprisingly. So you can make your own code zero allocation as well. But zero allocation is not a silver bullet. So since it avoids a heap, arguments often need to be copied to share data between functions. Copying large values on stack can actually consume more CPU even if no heap is used. The key takeaway is that zero allocation is just a strategy. Always measure the impact with benchmarks and use the zero allocation techniques wisely. So the message here is understand heap escaping and utilize zero allocation libraries wisely. So far, we talked about the heap, but now let's go back to the stack. So here we have a Stack Overflow, one of the most well-known programming errors. So it's a language, not an environment that sets a limit between the stack and a heap. So for example, on Linux today, the stack size in C is 8 megabytes. Calling too many nested functions, like shown in the slides, such as the infinite recursive loop, can exceed this limit and crash your program. And that's the Stack Overflow we all know. We've seen how heap escaping works and increasing the stack usage. And as you might also guess, the higher stack usage makes a Stack Overflow more likely. You might think the solution is simple, just prepare a huge stack area, right? It sounds good, but that comes with a trade-off. Allocating more stack space reduces the heap area, which can increase the chance of the OOM kills instead. And here is how Go solved the problem. Flexible stacks. In Go, each Go routine gets its own stack area, which can grow and shrink dynamically. So stacks are initially small, it's 4 kilobytes, and it expands as needed based on the Go routine stack usage. Here's a rough idea. So imagine the three Go routines, main and A and the B. A runs more code than other two and needs a larger stack, while main and B use smaller stacks, right? So Go handles this dynamically. So each Go routine only uses what it needs. Now, some of you may wonder how it is implemented. Originally, this was done by the segmented stacks, but this approach had limitations. Today, Go uses stack copying, the more optimized technique that quickly resizes stacks. So let's see how stack copying works in Go. Imagine this green box as a current main Go routine stack containing the main function stack frame and the M2 function stack frame. Now, if M2 calls M3, we need to add an M3 stack frame on the top. But as you can see here, it doesn't have enough space. What should we do? So Go detects a shortage now and allocates a new stack area for the main Go routine, double the previous size, in another area of memory. This upper box, represents the brand new main Go routine stack. Then all the existing stack frames are copied from the old stack into the new one, just like this. Once that's done, M3 can finally execute normally. And after returning from M3, the extra stack space is no longer needed, right? So Go just shrinks the stack back down. This dynamic resizing is what makes Go stack flexible, safe, and efficient for Go routines. Now, you might think that Go's flexible stack means Stack Overflow won't happen. But that's not true. Yeah, Stack Overflow still exists in Go. Each Go routine has a maximum stack size, which is 1 gigabyte by default. If a Go routine exceeds that limit, for example, with an infinite recursion in the function that I'm showing in the slides, Go will crash with a Stack Overflow error. So you see an error here, Go routine stack exceeds 1 billion by limit, and the fatal error, Stack Overflow. You can actually change the stack limit using a runtime /debug.setMaxStack function. However, since the default 1 gigabyte limit is sufficient in most situations, it is now recommended to modify it in the production. So flexible size stack per Go routine makes a stack in Go special. Understanding this also helps explain why Go routines are powerful. Now we're finally at the explanation of the example I mentioned at the start of the session. So as a reminder, this case shows that a single memory allocation change cut a CPU usage by 57% and memory usage by 99%. This amazing blog was written by the Honoka Toda, a Japanese software engineer at Cybernet. So now, first of all, please give her a big shout out. I really appreciate Honoka for giving this amazing blog. So what exactly happened in this article? So she noticed the periodic CPU spikes in applications like this graph. After digging in, she found that the app created many short-lived heap objects, which triggered the garbage collector many times. And using profiling tools, she eventually identified the bottleneck, the filtering function. Here's what the filtering function looked like before the optimization. It's a simple function that filters elements in the list and returns a new slice containing the filter function. And you can see here that it creates a new slice every time it is called. And the heap escape analysis shows it goes to the heap definitely. Since this function runs frequently, it generates a lot of garbage and triggers a GC repeatedly. After the optimization, the function reuses the existing slice passed as an argument instead of creating a new one. So I ran a simple benchmark comparing the original and the optimized filtering functions. So using a list of integers from 1 to 100 and filtering even numbers. So as you can see here, the optimized function was twice as fast. And what's amazing is that this improvement came from just a single heap allocation, only one slice. In this blog, Honoka went further by using iterator, making the logic safer and simpler. And across the entire workload, the optimization led to the 57% reduction in the CPU usage and 99% reduction in the memory usage. This is a perfect example of how understanding memory management can dramatically improve your application's performance. So that was a dense 30 minutes, and we're finally wrapping it up. So memory management has evolved to meet programmers' needs, and understanding it gives you the strong power to optimize your applications. The key takeaway here is this session is just the beginning. There are many kinds of more memory management sessions. So if you're curious, dive deeper into the concept to each concept and explore the memory management further in Go. So thank you all for listening, and I hope you enjoy the rest of the conference.